Hello, everybody, and welcome to another wonderful day of chemistry. So, today's kind of a quick little interlude as we're talking about molecular species. Because one of the things that is worth noting is that not all molecules are going to be composed of more than one atom. There is a small group of molecules known as elemental molecules. So these are going to be molecules that are composed of only a single element, which, not too surprising, means that they tend to have very simple empirical formulas because it's just the one element. But this also makes it very important to know what their molecular formulas are. So one of the most common is called a diatomic element. So these are going to be a molecule that is just two elements clinging onto each other in the wilderness. And there are seven elements that are commonly occur as diatomics. And these can be remembered using the rule of sevens. So what we do here is we can go ahead and start with nitrogen, atomic number 7. Then we go over and we make to fluorine and we go down, making a 7. It is worth noting fluorine's an easy place to think about because we go over to halogens, because after that, we're to noble gases, and noble gases like to be on their own. So we start with 7, go to group 7, and then go down to get a total of six molecules that look like a 7. Then we need a 7th molecule. So we go ahead and grab hydrogen because hydrogen likes to do its own thing. So all 7 of these molecules will tend to form diatomic elements. So as even the upperclassmen can tell you, it is important to remember when you're talking about things like molecular nitrogen or molecular oxygen to make sure to use the diatomic form. When doing problems, try and be very clear about when I'm talking about molecular oxygen, nitrogen, and the halides, and when I'm talking about atomic. So make sure to look for that word molecular versus atomic, as it's going to make a big difference on all your calculations because it turns out you're going to need to double your masses. So keep an eye out for that. But it is worth noting that while these are kind of the 7 big all stars for elemental forms, elemental molecules, there are a lot of other uh, molecules that can be formed out of a single element. One of the first things to watch out for, though, is allotropes. So, this is a fancy way of saying when a single element can make multiple different forms. So, one of the classic examples is oxygen. So, oxygen can form molecular oxygen or ozone. So, molecular oxygen is diatomic, and ozone, as in the ozone layer, is triatomic. And they have very different senses of reactivity. And it does help illustrate this idea that not uh, all elemental forms are going to be diatomic. Most elemental molecules are going to be diatomic, though. I also want to emphasize that allotropes can also exist for solid phases. There is a set of 3 allotropes that you are probably quite familiar with, as carbon has 3 forms. Mind you, they're all solid, so they don't fall under the molecular notation. But we have coal, which is carbon. We have graphite, as in pencil lead, which is carbon. And we have diamond, which is carbon. All of them are just elemental carbon. But anytime we have an elemental species that can take on different forms, that's going to be an allotrope. However, there are other allotropes that are molecules. So, another good example that you've actually seen has phosphorus. So, phosphorus is known for having 2 major allotropes. The first is a molecular species of white phosphorus, which is 4 phosphorus atoms linked together in kind of a pyramid. This is most famous for being used in explosives. So a lot of high-powered explosives will make use of white phosphorus as it's fairly unstable. However, there's another form of pseudo-unstable phosphorus, which is crystalline red phosphorus. So this is a crystalline phosphorus solid, and you probably know it from match heads. So it turns out in both cases, phosphorus would much rather react than it would to stay on its own. And we'll talk a little bit more about the reaction of phosphorus when we talk about combustion. For now, though, we're going to move on and talk about how we can try and determine all of these various molecular formulas that we've been talking about. And after that, we're going to put them to good use. Until then, take care.